In this chapter, we will be studying linear relations. In this lesson, we will be looking specifically at scatterplots.
Okay, hi everybody. So what we're going to do in this lesson here is we're going to take a look at scatterplots. What a scatterplot is usually just a bunch of ordered pairs plotted, and our goal is to try to determine what the relationship is, okay, between the two variables, between the x variable along the x-axis and the y variable, okay? So typically then what we're talking about here when we look at a scatterplot is we're talking about the correlation between the two variables. And we usually talk about the degree to which the data cluster around a straight line, okay? So usually the way we talk about that is the data here, the correlation is strong if you've got a clear line, okay? It's moderate if you can see the line, and we call it weak if you can't see the line, if there's no line of best fit that you can see clearly in that data, okay? So the line of best fit is what we're going to use to show a trend in the data. It does not have to pass through all of the data points. I've seen lots of people make mistakes like that, where they try really hard to get it to go through the data points, or they don't draw a straight line, they draw like a line that jumps back and forth between them. But we don't want to do that. But you do want to draw it so that you have about roughly the same number of points above and below the line, okay, as you go through. Now, when you come up with the equation of a line, please use points on the line. Don't use other points that are scattered through that you can clearly read. Use points that are on the line. Okay, that's the way you come up with the equation of the line. I can't come up with the equation of a line if I'm using points that aren't actually on the line, so please watch out for that. So then you have just a little bit of discussion here about what it means to be strong and weak and so on. Remember that an outlier is one that's significantly outside the main cluster. And then another thing that we're going to look at here is the data could be linear or nonlinear. Now we've talked about what that means. Linear basically means we've got a constant slope. Okay. Nonlinear means the slope is changing, or the slope varies as you go along the line here. Okay. Yeah, that's basically it. Now we're going to just jump in and do some questions here, and yeah, hopefully by the time we get to the end here, you'll get a sense of what it is that we're really asking you for here. All right, so in this question here, it says, for each of the following scatterplots, describe the linear relation, its direction, its strength, and identify any outliers. Okay, so right here, take a look at this one. When I see this, okay, first of all, I can see that there is definitely a trend in the data. It's going up, so I know that this is going to be positive. And in fact, there's actually a relatively clear line that you could kind of, probably should have pulled out a ruler when I did that, but there's a clear line that you can draw through that. So its strength is going to be, well, moderate to strong. Okay? I mean, it's not perfect, but I got a pretty good sense of what that line looks like, okay? And there are no real outliers in this data. Now, don't be grabbing little stuff like this that are just a little ways off here. An outlier should be significantly away from the rest of the data. Notice this as well, though. One of the things that I want you to think about here is if the data looks like it's pointed towards the origin, assume that it does go through the origin here. We're not going to be super picky about this. So we might also say that this relationship here is direct. Okay, it is, we're going to assume that it goes to the origin. Now let's take a look at this one. Okay, this one right here, well, it's still probably moderate to strong because I can really see what's going on here. It's easy to follow the line of the graph, but notice that in this case right here, it looks pretty clear that the graph is not linear. Okay, it is turning as you go up, or as you go along here, it starts to curve up here. Now we do have an outlier. This one point right here, this one is significantly away from the rest of the trend of the data, so we would call that an outlier there. This is still positive. Okay, I'll put this up here. It's still positive. It's going up. Okay, it's increasing as we go to the right, so that's good. Now, I realize what I just said here about going through the origin here, but when we talk about direct and partial variations, it's because there's a formula for the line that's being implied, and so we wouldn't typically use the expression direct or partial for something that's not linear. Let's take a look at the next one here. Now take a look at this data here. I think it's fairly clear given this point right here that the graph is doing something like that. Okay, now this would be a moderate correlation. Okay, there might be a little bit of variation between me and some other people how we might draw this. In fact, my line probably should be up a little bit. It's got a negative direction that it's pointing. Okay, it's dropping down. This is clearly an outlier here. Okay, and now because it is linear, okay, I can tell that it's linear. It's not curving like that other one did here. I might be able to look at this and say, well, this is going to be partial because it doesn't go through the origin. And then finally over here for this question, oh boy, this is all over the place. There doesn't seem to be any clear relationship between the data here, so I would simply say that this correlation, whoops, oh, I can't believe I spelled that wrong, is weak, and we just kind of leave it at that. Okay, I can't tell if it's positive, I can't tell if it's negative, because I can't tell what the relationship is. Okay, it's not clear if this is linear or what. So the best I can say at this point is that is a very weak correlation. Okay, now this question says, for each of the following, draw a line of best fit and determine its equation. Then using the equation, determine the value of y if x is equal to 20, and then determine the value of x if y is equal to 6. Okay, so let's take a look at this data here. First of all, I want to recognize that by looking at most of the data here, it looks like I've got this nice positive linear regression. This to me looks like an outlier, so I'm going to ignore that one. It does sort of look like the data is pointed towards the origin. So in this context, in this course right now, what we're going to do is we're going to assume that it does go through the origin. So I'm going to pull up my ruler here, put that there, and I'm going to try to make sure that when I draw my line of best fit, that I go through most of the points here. So I don't know, something like that. Yeah, that seems to be pretty good. So now there's my line of best fit. Now whether that's the best line of best fit, that's hard to say. We would almost need to get a computer to do that for us to get that perfect. But I'm just kind of getting a rough idea of the trend here. Now I want to come up with the equation of that line. Well, I know that it's direct, so I know that my equation is simply going to be y equals mx. So now I'm left trying to figure out what my slope is. So now, because of the way I've drawn this, I'm going to use the origin as one of my points when I'm figuring out the slope. So I've got the point 0, 0. Now I'm just going to go along here and see if I can find a point. Well, okay, I didn't really draw this through any of the points that I was given, so I might have to read one off the grid here. Oh, actually, you know what? That's a good one, right there. Let me grab this point right here. That is the point, and remember we use the x-coordinate first, so I go over to the 4 and then up to 3. So this is the point 4, 3. Okay. So, yeah. Now remember, this isn't a point that was given to me. I'm picking a point that's on the line. I'm not picking one of the dots that I see because they're not on the line. I didn't draw it through any one of those. So I'm trying to do the best I can here. So now my slope formula is going to be the y minus the y, so 3 minus 0, over the x minus the x, 4 minus 0. And I'm getting a slope of 3/4. So y is equal to 3/4 x. Okay? Now I can answer the two parts of the equation. I want to find y if x is equal to 20. Okay. So if x is equal to 20, this becomes 3/4 times 20. And that is going to be, when you go to your calculator and multiply that through, you're going to get 15. Now on the other hand, if I make y equal to 6 and ask for x, 6 is equal to 3/4 x. Well, I might multiply first both sides by 4. And so 4 times 6 is 24 equals 3x. And then I would divide by 3, and I would get that x is equal to 8. Okay, and there we go. Now let's do the same thing with this one here. This one, Okay, the data is clearly, again, it's linear again. I don't see any outliers. But in this particular case here, looks like, well, it's definitely partial. It's not going to be going through the the origin here. So I don't know. Let's pick a point here. I want to pick a. What I'm typically going to want you to do in this course here is I don't want you to fight too hard with the data here. So I'm going to grab a value on the y-axis that it appears to go through. And actually, because of the way that data goes here, I might just grab 4 because it's straightforward here. And I've got, so if I do 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, I can actually try something like this. If I do that, whoops, actually, probably looks better if I do that. Oh, it went a little askew there. Shoot, my ruler moved a little bit. Okay, so there's my line of best fit. Now, I should have gone through that point right there. So here's my first point. My y-intercept is going to be the point 0, 4. And then going along here, I don't see very many points that I can see clearly on the grid. But what I do see is I've got a point right there, and I've got a point over here. Now, my intention was to go through that point right there because it looked like it was going to keep an even number on both sides here. So that was the point 5, 2. It's partial, so I know it's going to have the form mx plus b. Well, I already know what the b is. I know that the b is 4. My y-intercept is 4. It's going to be plus 4. So now I'm stuck trying to figure out what the slope is. Well, slope is going to be y2 minus y1 over x2 minus x1. And don't be shy of those negatives there. So 2 minus 4 is going to be negative 2. 5 minus 0 is 5. So my equation, now that I've got my slope, is y equals negative 2/5 x plus 4. Okay, negative 2/5 x plus 4. And now I answer the questions that they were given here. What happens to y if x is 20? So y is equal to negative 2/5 times 20 plus 4. Okay. Well, 2/5 of 20 is going to be 8, and then there's a negative there. So it's going to be negative 8 plus 4. Well, the answer is negative 4. So what this means is this graph drops, and by the time I get to 20, I've dropped below the x-axis there. Now, on the other hand here, if y is equal to 6, that'll be negative 2/5 x plus 4. Remember how it works here. The first thing I got to do is get rid of that extra term. So I'm going to subtract 4 from both sides to bring that over. I see it's add 4 here, so I want to get rid of that. So I'm going to subtract. I'll get 2 is equal to negative 2/5 x. And then I'm going to multiply both sides by 5. 10 is equal to negative 2x. And then I'll divide by negative 2, and I'll get negative 5. Okay, and so there we go. There's the value of x. And using the line of best fit. Okay, so let's take a look at another couple of examples. Now you're going to see some repetition here, but that's kind of the point here. I want to make sure that you see some of the stuff over again. It says, for each of the following scatter plots, describe the linear relation, its direction, its strength, and identify if there are any outliers. Okay, so we take a look at this one right here. I think it should be fairly clear that that's an outlier. Okay, that data has very little to do with what's going on here. Now, this is a fairly strong correlation. There's a really nice line that kind of goes through, oh, and I didn't even do that right. I should have pushed that up a little bit here, but there's a really nice line that goes through there. It is negative, okay? And because it's a linear relation here, and it doesn't go through the origin, I can say that this is partial. So it's a partial linear regression, it's strong correlation, and it's a negative relation as well. Over here for this one, not quite so tight around a given line here. So this is, I don't know, this is moderate to strong. Okay, hard to say here. Now it looks like it's going through the origin, so I'm going to draw something that does that. Okay, that's not great, but you get the idea. So, but it does look linear. And so I would say, because it's linear and it does look like it's going through the origin, that it's direct. And the relationship here is positive because, okay, it's going up. Down here, yeah, this is all over the place. This is weak. I can't identify a direction. I can't identify anything really about that. It's just a weak correlation, and away we go. This one here, take a look at this one. This is a moderate, I would say, a moderate relation, but it's not linear. Okay, this is non-linear. If I try to draw a line through that, now granted I am going to go sort of through the origin and then it kind of swoops out like this. Again, I wouldn't think of it as direct because direct and partial imply equations, but this is not a line. Okay, but it's moderate to strong here, it's non-linear, and then we've got one outlier here that doesn't really fit with the group. And this is positive, okay? There is a positive relationship here. As the x values increase, the y values increase as well. Okay? Okay, everybody, so for this question here, we read that the following data compares the number of hours of a group of students spend watching TV per week compared to the number of hours spent exercising. Now, which is the independent variable and which is the dependent variable? Now, in a question like this, when you're asking a question, what depends on what? Does the number of hours you spend watching TV depend on the number of hours exercising, or is it the other way around? And in this case, I don't know. There really isn't a nice, clear relationship here. So basically, you got to make a choice here. And when it's up like that, I would make the top one here the independent variable, and I would make the bottom one here the dependent variable. Okay, so I'm going to put this along the x-axis. I'm going to put this along the y-axis. So now the question is asking me to plot this. So what I'm going to do here is I'm going to look at how my data grows here. Now for my hours watching TV, I go from 3 out to 32. And for my time exercising, I go, what have I got 13 to 2 here. Now, when I look at my grid here, I've got, what is it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, I've got 15 blocks there. So I have to kind of get my scale to fit that. So I might go up here along the y-axis by ones because I only need to go up to 13 for that. Along the x-axis here, if I go up by twos, okay, I'm just going to hit 30 right at the end here, and I'm supposed to go up to 32. Okay. So maybe what I'll do is I'll go up by threes. It's going to cut it down quite a bit, but that might be the best way to do that. So now I'm just going to take a moment and plot these points. If I did this in the video, it's going to take a lot of time, so just give me a second. Okay, and there we go. So I've plotted the points here. Now, I made a little bit of a whoops. I didn't notice one of the points here. This point right here has got an x-coordinate of 40. I didn't see that, but fortunately by going up by threes on here, I was okay. Now, we're supposed to plot the above points of the following grid and then draw a line of best fit. Now, when I look at this data here, actually, I'm really impressed that most of this data falls along a really clean line. In fact, this point right here seems a little bit out of kilter, as does this one. But the rest of them, if I ignore those, this seems to be a pretty good clean line here. And in fact, I'm going to just draw that in like that. And I like how that line looks there. Okay, when I look at it, I got 1, 2, 3, yeah, and then a couple of points that look like they're on the line. So that looks like a pretty good line of best fit. So now I'm going to flip the book over here to look at my question. For my first question is describe the data in terms of the strength and its direction. Well, this is definitely strong. Okay, strong, and once you ignore the, particularly once you ignore those 2 points that look like outliers here, and it's negative. Okay, so when time on one variable increases, the other one decreases, and vice versa. Now, what is the slope and what does it represent? Okay, well, I got to grab a couple of points here. So on my graph here, I'm going to grab 2 points, but it's got to be on the line. Okay, so don't worry about the points all around. It's got to be on the line here. So I've got a nice point right there, the point 0, 15. I like that one. Oh, gee, I've got a few of them here, but you know what? I'm hitting my x-axis here at 36. So my other point here that I might use is the point 36, 0. So I might just use those endpoints. I could have used this one nicely though too. This one that I've got here at 1210. That's a nice looking point. This one right here at 24.5. That's another good one. Whoops, 24.5. I should be able to use any of those, but I'm going to use these two extremes here. So 0, 15 and 36, 0. So for my slope here, where are we at here? I'm going to use the points 0, 15 and 36, 0. And so my slope is going to be 15 minus 0 all over 36. Oops, wow. Man, I immediately did that backwards. Because you got to go, it's this, if this point is on top, or sorry, if this point comes first, then it has to come first, numerator, denominator. So this has got to be 0 minus 36. So 15 minus 0 will be 15, and 0 minus 36 is negative 36. Now, when you take 15 divided by 36 here, what's common to both of those is a factor of 3. And so that negative can move out front here, and I'm going to get negative 5 over 12. Now, what does that mean? Well, what happens here, if the y-axis is hours of exercise and the x-axis is hours spent watching TV, okay, we lose 5/12 of an hour exercising for, actually, you know what? There's a better way to say that. I don't know why I'm making it as awkward as that. I'm just gonna back up. I'm gonna do that again. I'm gonna do this one again here. I'm gonna interpret this one more time here. So we lose 5 hours of exercise for every 12 watching TV. That's what that's saying here. So there's your rise, there's your run, or changing your rise, changing your run. So we're going to lose 5 for every 12 that we spend watching TV. Okay, and then the next question says, what is the y-intercept and what does it represent? Well, I used the y-intercept when I was finding the slope, so I already knew that. The y-intercept is 0, 15. Okay, so that's where the x-coordinate is 0 and the y-coordinate is 15. So what this means is if a student doesn't watch television, okay, doesn't watch TV, they will exercise 15 hours. Okay, that's what that's giving us here, because remember, this is hours of television watched, this is hours of exercise, and so when this is 0, this is 15. So, determine the equation of the line of best fit. Well, what I got here, remember, this is a partial, okay, this was a partial linear relation. So the equation is y equals mx plus b. And so in this case, y was equal to negative 5/12 x and then plus 15. So there's my slope, there's my y-intercept. Remember that I have to have the y and the x in there to make this an equation of a line here. And so now, from here, how many hours of TV watching correspond with 6 hours of exercising time? Okay, well, exercising time is my y, so I'm going to make that 6, negative 5/12 x plus 15. So now I'm going to subtract 15 from both sides. I want to get this term with the x by itself. I'd like to be able to get x all alone so I can solve for it. So I got to get rid of this thing first. I'm going to subtract 15 from both sides. So if I do that, okay, it cancels over here, then 6 minus 15 is going to be negative 9 is equal to negative 5/12 x. And then I'm going to multiply through by 12. Okay, so negative 9 times 12 is going to be negative 100, whoops, oh shoot, 108 is equal to negative 5x. And then 108 divided by 5, because I got to get the x by itself, is going to be 21.6 hours. Okay? At least that's what it says. Now, the last question here says, how many hours of exercise correspond with 30 hours of TV watching? That one's actually a little bit easier to do, because all I got to do is plug in a 30 in for the x. And then I can easily evaluate that. So it's going to be negative 5/12 multiplied by 30 plus 15. And I can just enter that in my calculator in one sweep here, and I'll get to 2.5 hours.